Hi dear students, welcome back to e-learning class. I am your professor Santosh J. Dear students, as you know, in previous class we discussed about the model 3. In model 3 we discussed about polymer materials, classification of polymer materials, as well processing techniques of polymer materials. Today I am going to teach you the continued part of that model 3. The today topics are powder metallurgy concept, powder metallurgy basic steps, and the present and future tense of powder metallurgy, as well as history of powder metallurgy. Okay dear students, let's discuss in detail one by one. Yes, now I will start with the introduction of powder metallurgy. Yes, a powder metallurgy is a manufacturing of shaped components or semi-finished product from metallic powders. A powder metallurgy is preferred due to its product cost effectiveness. The main factors are low energy consumption, high material utilization, production of complex shapes, and product uniqueness can be obtained by combination of materials which otherwise would be impossible to mix. Hope you understand the introduction. Now, in the introduction part only, we come to know what exactly the powder metallurgy. Yes, definition of powder metallurgy. The powder metallurgy is a process of blending fine powdered materials, pressing them into desired shape or form, and then heating the compressed materials in a controlled atmosphere to bond the materials. I repeat, is the process of blending the fine powder materials, pressing them into a desired shape or form, and then heating the compressed materials in controlled atmosphere to bond the materials. The final component is usually does not require further machining processes. 5 pm, which means what's the importance of powder metallurgy technique? Because PM parts can be mass produced to net shape or near net shape. The PM parts have a doctoral properties, no need for subsequent machining in PM parts. PM process wastes very little materials, up to 3%. The rest of the 97% will be utilized. PM parts can be made with a specified level of porosity to produce the porous metal parts, for example filter, oil, impregnated bearings and gears. Looking to the history of powder metallurgy, the early Egyptians made metal products by application of powder metallurgy principles as early as 3000 BC before the Christ. In the year of 1829, an Englishman made a ductile platinum by cold pressing and sintering. In the year of 1870, Irvan Welsbach prepared osmium filament by using the powder metallurgy technique. In the year of 1916, the first commercial tungsten wire was produced by this powder metallurgy technique. A powder metallurgy was used in Germany for producing the tungsten carbide tooltip after the First World War. The powder metallurgy becomes widely recognized after in the year of 1945 and today. The parts which cannot be formed using other processes are made using this process. Okay dear students, let us discuss with the basic process of powder metallurgy. The basic process of powder metallurgy, which involves 4 basic steps. Number 1, powder manufacturing. Number 2, mixing and blending. Number 3, compacting. Number 4 is sintering. As we can see this flow chart, this is the simplified flow chart of the basic powder metallurgy process. See one by one. So here we can see the alloys and metal powders, and the left side we can see the additives or binders which are mixed into the blending process. Up to the blending process, the powders are coming to the compact process. After compacting, the materials will that produced component will come into the sintering process. After sintering, this process have two options before finishing. The one is optional secondary manufacturing, second is optional secondary finishing process. After this, the finally finished PM parts will be achieved. Okay, dear students, we will discuss next in detail each four steps. Yes, the first step is powder manufacturing. The property of the powder metallurgy products have highly dependent on the characteristics of starting powders, which means starting powders, and underline starting powders. Before selecting that powder materials, we should take care about their characteristics, because that is going to affect performance of our finished product. Here we sort out some important characteristics of the selected powders, some important properties and characteristics of the given powders are selected powders. One is the chemistry and purity, particle size should be an equal and same, and size distribution, particle shape and surface structure. Hope you understand. Such kinds of the importance are very important while selecting the powders, and useful in producing the pre-alloyed powders. Each powder particle can have the desired alloy composition. Hope you understand. Once you use the pre-alloyed powders, each powder particle can have a desired alloy composition. That's very, very important. So continue. The majority of commercial powder is produced by some form of melt atomization. Dear student, atomization is a process where liquid metal is fragmented into a small droplet that cools and solidified into particles. As we can see, there are two images on the slide. The two methods, which means the two methods for producing the metal powders. As we can see right side, image A, the melt atomization, and as we can see the left image, the atomization from rotating consumable electrodes. Let me to clear how these two methods are work. So here, as we can see, the ladle full of a liquid powder. This liquid powder is poured into the atomization chamber. The inside the atomization chamber, which provides two nozzles, these two nozzles strike the liquid powder. Once the liquid powder is struck out, it's turned into a small droplets. Those are fed into the bottom collector, then that cool and solidified into a small particles. Hope you understand how it works. And at the left side, that is second image B, the atomization from rotating consumable electrodes. Here we are using some consumable electrode that should be fixed into the spindle, and it should rotate by means of spindle rotation. So here we have to pass the molten metal into the chamber. Once the molten metals are strike the spindle is strike out the molten metals by means of rotating. Once the particles are struck, they turn into a small droplets. That droplets are which are then fed into the bottom side, and here the vacuum chamber is subsequently to suck the hot airs or moisture air present in the chamber. Once those are cooled and solidified, we will get particles, powder, small powder particles at the bottom side. Hope you understand how it works. And okay, the additional methods which we are involving, rather than these atomization process, which we are using the another additional methods for producing the powders, so called powder manufacturing, and some other techniques here I list out. One is a chemical reduction of particulate compounds and electrolyte deposition, pulverization and grinding process, thermal decomposition and particulate hybrids, and precipitation form solution, condensation of metal wafers. Almost any metal or alloy can be converted into a powder by using such kinds of the methods. The next concept is rapidly solidified powder particles. So which means crystallines and amorphous materials which we are going to produce the rapidly solidify the powders, which we can get the crystalline, solids and amorphous if the cooling rate of an atomized liquid is increased. Ultrafine or microcrystallized grains can form. Hope you understand, dear students. If the cooling rate of an atomized liquid is increased, its ultrafine or microcrystalline sized grains can form. These are the strongest grain finite. This is the good method. And some metals can solidify without becoming a crystalline solid, so called as an amorphous materials. These amorphous materials are less good as compared to that of microcrystalline solid particles. The amorphous materials can have a high strength, improve corrosion resistance, and reduce the energy into induce and reverse magnetization. And powder. The next step is the powder testing and evaluation. Powder testing and evaluation is very important to evaluate the selected powders for the desired properties of finished product. The powder should be evaluated for their suitability for the further processing. Number 1, flow rate, which measures the ease with which powder can be fed and distributed into a die. And second one, apparent density, is the measure of a powder ability to fill available space without external pressure. Third one, compressibility, is the effectiveness of applied pressure. The green strength, which means is used to describe the strength of the pressed powder after compacting. These are the evaluation steps of the powders. Yes, powder mixing and blending. The other term is powder mixing and blending. The majority of powders are mixed with other powders, binders and lubricants to achieve the desired characteristics in the finished product. A sufficient diffusion must occur during sintering to ensure a uniform chemistry and structure. The unique composites can be produced. Blending and mixing operation can be done either wet or dry technique. Yes, now come to the next step is compacting. Loose powder is compacted and densified into a shape is known as a green compact. Most compacting is done with the mechanical presses and rigid tools. For example, hydraulic and pneumatic pressures are also used to compact the powders. So dear students, as we can see the chart here, this is a typical compacting pressure for various applications. Now we can take a first application is porous metals and filters. For this, which we can take the compaction pressure in terms of megapascal, 40 to 70 megapascal. Second example is refractory metals and carbides. Here we can take a 72 to 100 megapascal. And third application, porous bearings. Here we can take 146 to 350 megapascals compaction pressure. And fourth application is machine parts, medium density iron and steel. Usually here we can take a compression pressure 275 to 690 megapascals. High density copper and aluminum parts, here which we can take a compaction pressure is 252 to 75. And high density iron and steel parts, in these applications which we take a compaction pressure in 690 to 1650 megapascals. Hope you understand a typical compacting pressure for various applications. So here we go. As we can see the image, both the image are explaining us to the compacting machines. So in the left side, what we can see, the typical pressure for the compacting of metal powders. And here we can see the left side is a removable die set, allows the machine to be producing the parts with one die set while another is being fitted to produce the second product. Yes, compacting sequence. Let me to explain how the compacting sequence begins. Okay, a powder do not flow like a liquid. They simply compress until an equal and opposing force is created. Hope you understand. The powders do not flow like a liquid. They simply compress until an equal and opposing force is created. This opposing force is created from a combination of one, resistance by the bottom punch, and two, the friction between the particles and die pressure. As we can see the image, dear students, this is the sequencing process. The first image, as we can see, it's indicate that arrangements of compacting machines. Here we have some parts. One is a punch 1 and punch 2, and feed shoes and dies. This is the first images indicate that arrangements of compacting machine, and second images indicate that charging die with the powder, which means the feed shoes are continuously feeding the raw materials or powders into the die. Now the die is completely filled with the powder materials. And the third image is indicate that compression begins, which means after completing the entire die cavity, now the compression is begins by means of hydraulic or pneumatic pressure. And the image 4 indicates that compression is completed. The required shape and size of the finished product is being ready inside the die. The compression process is completed. And the fifth image is indicate that ejection pin. Once we achieve the required shape, now we have to remove the ejection pins to dismelt the arrangements. And sixth image indicates that to collect the finished product by filling the raw materials into the die for the next process, so called it is recharging of die. Hope you understand. And complex in compacting, it's a very important term. It is, if an extremely complex shape is desired, the powder may be encapsulated in a flexible mold, which is then immersed in a pressurized gas or liquid. So it's known as a isostatic compaction. In one compaction, the powder is heated prior to pressing. The amount of lubricant can be increased in a powder to reduce the friction. Because the particles tend to be abrasive, the tool wear is concerned in powder forming. Yes, sintering process. The next step is a sintering process, which is a very important basic process. In the sintering operation, the Pressed powder compacts are heated in a controlled atmosphere to right below the melting point. There are three stages which are involved in the sintering process. That number one is a burn off. The combust of any air and removes the lubricants or binders that would interface with a good bonding. The second is the high temperature desired solid state diffusion and bonding occurs. And third step is cooling period. The lowers the temperature of the product in a controlled atmosphere. All these stages must be conducted in oxygen free conditions. Let us discuss the hot isostatic pressing in powder metallurgy process. The hot isostatic pressure HIP combines the powder compaction and sintering into a single operation, which means the gas pressure squeezing at a high temperature. The heated powders may need to be protected from the environment, harmful environments. The products emerge at a full density with uniform isotropic properties, which means near net shapes are possible. Next, we discuss the other techniques which we are going to use to produce the high density PM products. As shown, dear students, as shown in the figure, the one method of producing the continuous heat products from the powder materials. As we can see, there is a powder hoppers is there, which continuously supply the powders into the two rollers. The two rollers are compacting that powders to form a thin sheet. That form thin sheet is which are fed into the sintering furnace. The sintering furnace to maintain the temperature of the thin sheets and as well as to remove the moisture content present in the or additives present in the powder materials are burn out in this process. After sintering process is done, these two rollers are fully sheets from the furnace and which are fed into the cooling system. Now the cooling process is done. After cooling process is done, which we can collect the finished product in the form of sheets. One more method to produce the high density products from the PM, that is metal injection molding MIM or powder injection molding PIM. As we know all the powder injection molding process in previous class, there is no need to take once again. It is because we know all the how the injection molding process begins. The ultra fine spherical shaped metals, ceramics or carbide powders are combined with a thermoplastic such as the wax materials and becomes the feedstock for the ejection process. The material is heated to a paste-like consistency and ejection into a heated mold cavity. After cooling and ejection, the binder materials is removed and finally we can get the finished product from the injection molding. Now the the next image indicates that the left side figure is indicated that flowchart of the metal injection molding process MIM is used to produce the small intricate shaped parts from the metal powder. The right side figure indicates that metal injection molding is an ideal for producing the small complex parts as you can see on the slide. Okay, dear students, how it works, just look into the flowchart how MIM works, how the sequence begins. It's just similar to the powder metallurgy sequence. MIM means injection molding. How the injection molding takes place, the same way to MIM is also processed. The first one is the fine powder particles and binders are mixed into a mixing and pelletizing method. After pelletizing, the powder materials are fed into the injection molding. Which means the ejection process will be done. After ejection process will be done, we are going to remove the binders by the sintering process. So once the sintering process is done, all the binders and additive materials are removed out. After sintering, which we are going for there are two optional operations. One is a finishing, another one is a manufacturing. Now we will go to the finishing operations. After the finishing operation is done, which we can get the finished product, as we can see on the slide. I hope you understand how MIM is work. And coming to the next topic is secondary operations. What is the need of secondary operations? What exactly the secondary operations which we can deal with in these slides. The most popular powder metallurgy products are ready to use after the sintering process. Hope you understand. Most powder metallurgy products are ready to use after the sintering process. Some products may use secondary operations to provide enhanced precision, improved property, or special characteristics. Hope you understand. Some products may use secondary operations to provide enhanced precision, improved property, and special characteristics. The distortion may occur during the non-uniform cooling down, so the product may be repressed, coined, or sized to improve dimensional precision per the dimensional requirement. So in such conditions and such situations which we can use the secondary operations. Hope you understand. Continue. If massive metal deformations takes place in the secondary pressing, the operation is known as a PM forcing. Increases the density and adds the precision. Infiltration and impregnation of oil or other liquid is forced into the porous network to offer the lubrication over an extended product lifetime. The metal infiltration fills in a pores with other alloying elements that can improve the properties. The PM products can also be subjected to the conventional finishing operations such as heat treatment, machining, and surface treatment. Now we will discuss the properties of PM products. The properties of PM products depend upon the multiple variables, which are type and size of the powder, amount and type of the lubricant, and pressing pressure, sintering temperature and time, finishing treatment. The mechanical properties are depending on density. Product should be designed so that the final properties will be achieved with the anticipated final porosity. Yes, these are the materials which we can use to produce the PM parts, which are iron, steel, stainless steel, and aluminum, copper, and brass. As we can see on the chart. Yes, design for the powder metallurgy parts. So basic rules for the design of PM parts. Number 1, the shape of the part must permit ejection from a die. The powder should not be required to flow into a small cavity. The shape of the part should permit the construction of strong tooling. The thickness of the part should be within the range for the which PM parts can be adequately compacted. The part should be designed with as a few changes in the section thickness as possible. Okay, let's come to basic rules of PM parts. Dear students, the parts can be designed to take advantage so that a fact that certain forms and properties can be produced by PM that are impossible, impractical, or uneconomical by any other methods. The design should be consist with the available equipments. The consideration should be made for product tolerance. The design should consider and compensate for dimensional changes that will occur after pressing. Dear students, as we can see the image on slide, the example of a poor and good design features for powder metallurgy products. Recommendations are based on the ease of pressing, design of tooling, uniformity of properties, and ultimate performance. as no is indicates that a poor design and yes is indicates that a good design. So however, we can see on the slide, this is a second image, this is the no means a poor design and yes means a good design. So I hope you understand, wherever yes is there, all that designs are good designs. Where is a no is there, those are all the bad or poor designs for the powder metallurgy products. Now coming to the powder metallurgy products, the porous or permeable products such as bearings, filters and pressure or flow regulators. These are the powder metallurgy products, and products of complex shapes that would require considerable machining when made by other processes. The products made from materials that are difficult to machine are materials with high melting points. The products where the combined properties of two or more metals are desired through the powder metallurgy techniques. The products where the PM process produce clearly the superior properties. The products where the PM process offers and economic advantages. And the advantages and disadvantages of powder metallurgy. The advantages are which are elimination or reduction of machining, high production rates, complex shapes, wide variation in composition, a wide property variation, scrap is eliminated or reduced. Disadvantages: inferior strength properties, high tooling costs, high material cost, size and shape limitations, dimensional changes during sintering, and density variations, and health and safety hazards. Hope you understand the advantages and disadvantages of powder metallurgy technique. Okay dear students, now I will stop this session. We will continue left out topics in the next session. Thank you.